Hey guys, welcome to today's Sunday contest. I was able to solve all the problems and we'll make a tutorial for the third problem. But for the fourth problem, it was kind of like if you know a particular concept called matrix exponentiation, then that would be easy to do, right? So I'll just share a blog which you guys can go through, and then if you guys request, I'll make a separate video explaining the whole matrix exponentiation trick. Okay. So let's get started with problem number 3. So problem number 3 states that we are given a integer n, l and r, three integers, and what you want to do is what you want to do is count the number of zigzag arrays. So zigzag is because an integer can lie in the range from l to r. Okay, so let's say you have an integer n, l and r. Okay, let's say on the first position you decide to put a. Okay, so in the second position you can put b. You can put your two choices to put b. Your b, like, it can be less than a or b can be greater than a. Okay, because the condition is no two adjacent elements should be equal. And then third condition is that no three consecutive elements form a strictly increasing or strictly decreasing sequence. Okay, so this implies if you go ahead with this condition, okay, then your c should be strictly less than b. Okay, because if c became greater than b, then what would happen? If c greater than b, then what would happen is you would get a sequence like this: a, b, and then c. We don't want this because this is strictly decreasing, right? Strictly increasing. Yeah, and strictly increasing we don't want. So this is out of the question. We cannot put this. And similarly, if you put like a is less than b, then you can put c. C should be greater than b, right? Because if you put c less than b, then what would happen is that you get a, b, and then okay. Sorry, my bad. What am I doing? I think I messed up. Sorry. Let me go again. Yeah. So a is greater than b. So your c should be like less than b, right? Right. A, b, and then c is always less than b. And if you do this you cannot do, right? Because c is like less than b, and you get a strictly decreasing sequence, which we don't want. So actually c should be greater than b, right? So in that case, what would happen is a greater than b, and then c should be greater than b again. So like this you can do, right? This we cannot do because it's a strictly decreasing sequence. And similarly here c should be less than b. Okay, because you cannot have a sequence like this where c is greater than b, right? We cannot have this, but we can have this: a less than b, and then c is less than b again, like this we can have. Okay, so this is what I'm doing here. Okay, so from here you can define a dp. So dp, so you got only two states to define: dp of I, j, and k. So I is the current index, j is the values that your current index can take, which is in the range of L to R, and k is if my previous value is like 0 or 1. So it's basically 0 or 1. So let's say you are standing at index I, okay, and let's say your k standing at index I, and you put a value j over here. Okay, so now let's see this. So you can have two states, 0 and 1, which is k. Okay, and then b. So let's say we are considering this case, j less than b. So b is a previous element, so I minus 1, let's say we have put b over here. Okay, and we are taking that zero state is saying that this guy should be less than this guy. Okay, that should be less than this guy, and 1 is saying this guy should be greater than this guy. Okay, that's what your states mean. Cool. So now, according to our previous state logic, what we saw was that if dp of I j 0, if we do it like this, I j 0 means j should be less than b. So this is nothing but summation of dp of I j dash and then 1. Okay, 1 because j less than b is basically this condition. Okay, so you need to have yeah, you need to have this condition as well, like c is less than b, so j is less than b, so c, I think c is j over here. Okay, and yeah, so you just put 1. So 1 is saying that I want my previous, so let me explain this a bit more. 1 is saying that let's go to state I minus 1, let's put a j dash over here. Okay, and let's put a 1 over here. Okay, because we want to alternate it, right? Because if you put a j, that means, and it's a state 0, that means your array is looking like this, b and then over here. Okay, so you cannot have this thing going on, right? You cannot have this sequence because it will become strictly increasing. What you can have is this sequence a, b and then j. So now this is basically state 1 for j dash. J dash is my b. Okay, so let's put a b over here, not j dash, so it will be more clear to you guys. B and then 1. So 1 is saying my a should be greater than b. Okay, so my b is like this is the element at I minus 2 basically. That should be greater than b. That's what state 1 means, right? Your previous element, like your current element, is greater than the previous element, right? So just do that and you sum overall possible b, right? So now since it's a state 0, your b is less than j, right? Sorry, your b is greater than j. Since it's a state 0, your b is greater than j, so range of b can go from j plus 1 to r. So I'll just write a range of b over here, j plus 1 to r, and the range of b for this guy is L to j minus 1, right? So when you do a summation, it would go from j plus 1 to r, and similarly we'll write the other case, dp of I j1 should be this, the mirror, like dp of I minus 1 b, and then you put a 0. So this should go from L to j minus 1. Okay, so these are your dp states. I'll just explain this condition again, this one. So this is saying that, okay, let's put j and 1. So my j is at state 1. So this is like this, array is looking like this. So j and b. So this guy is greater than this guy, okay, because that's what state 1 means. So you cannot have a less than b. You cannot have you cannot have this condition. Okay. Okay, just a sec. Yeah, state 1 is saying j is greater than b. Yeah, you cannot have this condition. So just give me a moment. A should be greater than b and b should be less than j. Yeah. So this guy, we cannot have this condition obviously, okay, but we can have this condition. This condition is valid. So a greater than b, meaning that you shift left, like to the previous element, I minus 2, I minus 1. So what is this state? Is this state 0 or is this state 1? What is this state? The 0 state implies that your current element should be greater than, so less than the previous element, one state implies that your current element should be greater than the previous element, should be less than the previous element. So 0 is current is less than previous, current is 1 is current is greater than previous. So in this case, B is your current and A is your previous. So previous is greater than current, which is state 0, right? This is the same. So that's why you put a 0 over here. Okay, and then B is again, yeah, B is saying that okay, I'll be less than J. Okay, so I need to go from L to J minus 1 and sum it up. So you can do a fast summation on this by storing in a prefix sum array. Okay, so I'll just define a prefix sum, because time complexity right now, if you do it naively like this, would be n times L to R times, because B can vary from L to R again, right? L to R times 2, right? So that's like around 10 is to 9 operations, right? Okay, so that's not acceptable. That will give you a TLE. So you can speed it up using prefix sums on B. Okay, because B is just L to J minus 1, and yeah, you can just speed it up using prefix sums. So yeah, hope that explains that. Prefix sum is very basic idea. So P of I, you can store P of ij0 is just a summation of dP of I j dash 0. So j dash belongs from L to R, okay, and sorry, not L to R, but L to J, okay, because we want to prefix sum till J. And similarly, P of I j1 is summation of all the dPs from L to J again, dP of I j dash 1. So how is this beneficial? This is beneficial because now you can do a range trick where the dP is self-defined. Okay, so I'll just show you in the code, it is more self-explanatory. That's what I'm doing. Your dP in prefix sum is defined. Initially everything is set to 0. Then dP of 0 I0 is like 1, because you can at the first position you can put any element between L and R, right? So you'll always get one possible array, right, in both the cases, right? Because previous element doesn't matter, 0 and 1 doesn't matter, so for both of them you will put prefix sum. Again, I defined like the previous prefix sum is like just normal prefix sums, okay, and then the states. Okay, so dP of ij1 is, yeah, dP of ij1 plus prefix sum till I minus 1 j minus 1 0. So j minus 1, because this will encompassate all the range from L to j minus 1. Okay, that will work like that. And here for 0 case we have P of I minus 1 j1 and total minus that, because we want to go till R, okay, and then subtract everything till J. Okay, I'll just show that. So J is, let's say, looking like this. Okay, so for doing this case where you go till R and subtract everything till J, value till R, value till J. Okay, so this is how you do that thing. Basically, you want to calculate this state, right, J plus 1 till R. So this would require that thing where we are subtracting the total minus all the summation of all the values till J. Okay, that will give you the values till from J plus 1 to R. So yeah, that's what I'm doing, and recalculate the prefix sum for the current state again. And for the answer, okay, for the answer is like you reach till n minus 1, you can put any value L to R. So you want to calculate a summation of all of them and then return the answer. Yeah, so that's it for the third problem. And for the fourth problem, it was a similar idea, but just the states were like till 75. So this is a very standard matrix exponentiation problem. So I'll not go into much depth here because it would require, the video would get very big, but I'll just link this resource, matrix exponentiation tutorial, where problem number D, if you try to solve, or even problem number I, okay, you get the idea of how you can optimize this more using matrix exponentiation. Okay, cool guys, thank you for watching, and yeah, bye.